Introduce our first speaker. Her name's Emma Mitchell. She's a fifth-year Ph.D. candidate in statistics at the University of North Carolina in Chapel Hill. She concentrates in methodological advances in the analysis of genomic data using Bayesian modeling and multi-view data integration techniques. She also spent a summer here as an intern at IDA, and she's bringing her Bayesian expertise here. And today she'll be sharing that with the rest of us. So without further ado.
Fancy. Okay, can you all hear me okay? Sounds good. Okay. So today I'm going to be talking about a reliability assurance test planning and analysis tool I developed over the summer as a summer associate here at IDA. And this was joint work done by myself and my mentors, John Heyman, Rebecca Medlin, Curtis Miller, Drew Patel, and Caleb Pagan-Rivera. So lots of chefs. Okay, and kind of the big question that we wanted to answer here is, how long should we test a system for to adequately assess system reliability? And as we know that traditional approaches often require very lengthy test durations, and thank you. So sorry about that. The idea is that if we incorporate prior knowledge about the system into the test planning process, then we can hopefully reduce the required amount of testing necessary. And so the problem with this is there is currently no user-friendly software to perform this kind of analysis, and so that's where my project came in. I developed an R-Shiny app for the Test Science website, which both plans for a Bayesian assurance test, and the Bayesian assurance test we're going to talk more about in this presentation. It's what incorporates the prior knowledge of the system. And also, we're going to use this app to analyze analyze data from a Bayesian assurance test. Okay, so before I get into the nitty-gritty of what a Bayesian assurance test is and why we should use it, I want to take a step back and talk about something we're probably all familiar with, and that's what is reliability. So reliability is the probability that a system performs its intended function under operating conditions for a specified period of time. And for the purposes of this presentation and just the app in general, I'm going to focus on the reliability quantity of interest here, which is the mean time between failure. And as someone who has a crippling fear of elevators, an example that I like to give is we want an elevator to be reliable, meaning it should consistently operate without getting stuck during normal usage over time. And so this is really important to us, right? An unreliable system, like a faulty elevator, may impact the mission and may make you late to work, resulting in error, delays, or even accidents. And so the idea here is that if we plan a test with reliability in mind, we can hopefully prevent against having an unreliable system as our end product. So for the purposes of this presentation today, we're going to talk about this case study, which is testing a new variant of a cargo helicopter. And this cargo helicopter, for the purpose of this example, supports a variety of operations such as air movement, casualty evacuation, aerial recovery, and area resupply. So it's really important that the system is reliable. And some pieces of information that we want to extract about this system is the reliability requirement, which can be found in the system documentation, and that's a mean time between failure of 35 flight hours. We're also going to need the reliability objective, which here is a mean time between failure of 70 flight hours. And then because we're using a Bayesian approach, we also need prior information about the system to hopefully get those benefits of reducing the required amount of testing. And that's going to include 329 flight hours and 7 observed mission failures from developmental testing. And then additionally, because we know from the literature and just previous experience that there are some system changes when using DT data to plan for OT, we are also going to incorporate an estimated 10 to 30% decrease in reliability. And I'll show you how that gets baked in. And so the thing that we're going to answer today is how long should we test the helicopter for, and what are the maximum number of failures allowed when demonstrating the requirement with confidence. So typically evaluators would pull from something called a reliability demonstration test, which uses only the data from the current test to assess whether the mean time between failure meets or exceeds the requirement. And here the test length for a reliability demonstration test is going to be informed by your reliability requirement that we just talked about, the system's true underlying reliability, and then the risk we are willing to accept in making an incorrect statement about the reliability of the system. And so typically you can visualize different test plans from a reliability demonstration test using something called the operating characteristic curve, which you're probably familiar with, or you may have heard it called the OC curve. And an example of an OC curve, or several OC curves from this case study, would be here in this plot, where the x-axis is the true underlying mean time between failure and flight hours, and the y-axis is the probability of acceptance. And here the dashed lines represent the reliability requirement and objective that we just talked about. So if we focus in on that shortest test plan, which is the curve that is in dark blue and is 105 hours of required testing, you can see to demonstrate reliability to have a high probability of demonstrating reliability, we need a true mean time between failure of around 95 flight hours. And so that's very unlikely, right? That's greater than even our objective going into the study. And so to make a more likely assumption, we would need more hours of testing. For example, this orange curve, which requires 277 hours of testing. And so the big takeaway here is that a reliability demonstration test can require very lengthy testing periods or a very high true mean time between failure assumption. And so this is why we suggest using something called a Bayesian reliability assurance test, which uses contextual information about the system with the goal of reducing the required amount of testing. And so here, contextual information is going to include earlier test results on same or similar systems. So that's exactly what we're doing here when we incorporate DT data into our test planning process. It can also include expert judgment regarding performance, knowledge of the environmental conditions under which the system are used, and then prior knowledge of possible failures. And then additionally, we suggest that you should use a Bayesian assurance test if, or it works best when, there are minimal system changes expected between testing, longer previous testing periods so you have more data, and then lastly, if a reliability demonstration test is just, the test plans from that is just not feasible, then perhaps if you have previous test data, you could also try using a Bayesian assurance test. Okay, so there are kind of two big outcomes from the case study. The first is that for this example, a Bayesian reliability assurance test plan, all of them were more efficient than the traditional reliability demonstration test plan. And so if you look at this plot, the x-axis is the number of allowed mission failures from both the Bayesian assurance test plans and the traditional reliability demonstration test plans, and the y-axis are the prescribed number of flight hours from each of those test plans. And so you can see that in all cases, the traditional reliability demonstration test required more testing. And then kind of the second outcome here is that if we observe a test exactly like what we planned for, the interval produced by incorporating previous test data, shown in blue, is always contained within the interval constructed using traditional methods. And so this means that incorporating previous test data reduced the uncertainty around the mean time between failure estimates and gave us a better, more intuitive understanding of the helicopter's reliability. And so kind of the big takeaway is, like, if you plan for a test using Bayesian methods, you should also analyze data from that test using Bayesian methods as well. Okay, so I kind of talked up front about the benefits of using a Bayesian approach to test planning, but what are the steps, what are the ingredients that we're going to need to perform to plan for a Bayesian assurance test? So the first thing you're going to need, like any Bayesian analysis, is to define the prior, likelihood, and posterior. So here we assume, before we've seen any data at all, that the mean time between failure is inverse gamma distributed, and this is an uninformative prior, although we know no prior is truly uninformative. We also assume that the between failure times are independent and identically distributed according to an exponential distribution with constant failure rate 1 over the mean time between failure. And then lastly, we can form our updated belief using Bayes' theorem about the mean time between failure given that developmental testing data. And that's because we chose a conjugate prior, going to also be inverse gamma distributed. So the big takeaway here is that the posterior is the updated distribution of the mean time between failure given that supplemental data that we have, and it's going to serve as our prior belief about the mean time between failure when we solve for a test plan in this Bayesian assurance test planning process. Okay, so the next ingredient that we're going to need is we want to determine whether a change, meaning degradation or improvement, is likely when using one testing phase to plan for another. And so we know here in this case study we're using DT data to plan for OT, And we happen to know that in DT, it's usually conducted in a more controlled environment, tested by non-operationally representative users, and testing is often longer. Versus in operational testing, it's on production representative systems conducted in an operationally realistic environment and often tested by real users. And so we have to figure out a way to incorporate these differences into the planning process in order to make use out of this DT data. And so to account for this, we add a multiplicative correction factor, D, which we assume follows a gamma distribution, and we multiply that by our distribution, our posterior distribution that we just talked about of the mean time between failure given that DT data. And so if you look at this plot that is visualized here, you can see that the red distribution is the adjusted posterior distribution after degrading it, versus the blue is what the original distribution of the mean time between failure given our DT data was. And this is a really important step because failing to incorporate this degradation factor could lead to inadequate test plans that don't require a sufficient amount of testing. Okay, so then after that, the next key ingredient is to determine the maximum amount of risk you're willing to take. And before I talk about the different types of risks here, I want to say that these risks depend on this concept of passing the test or failing the test. So here we say that a system has passed the test if we observe C or fewer failures in total operating time T, where C and T are defined by your test plan. And then the opposite is true. If we fail the test, that means we observe more than C failures in total operating time T. And so there's kind of two risks that we can take here. The first is called the posterior producer risk. And that's the risk of having a mean time between failure, which is greater than the objective, given that we actually know the test has failed. And then the second type of risk you can take is posterior consumer risk, which is the risk of having a mean time between failure that's below that requirement we set ahead of time, given that, in fact, the test has actually passed. And so these are the mathematical formulations here, and we want to cap that risk. And typically we see that these risks are capped at around 20%. For this example, which was based on a real data analysis, we capped that posterior producer risk at 30% and posterior consumer risk at 20%. And you can see that in these equations, you're going to need something called P of theta, and that's our prior belief about the mean time between failure. And this is exactly where your developmental testing data gets baked in here. You can replace P of theta with that updated belief about the mean time between failure given your developmental testing data. And then if you had a degradation or improvement factor, that's exactly where that would get baked in as well. Okay, so then once we have these equations, we can solve for a test plan, and it's essentially just solving those systems of equations. So from here, it's pretty simple. For each number of failures you're willing to consider in your test plan, the chosen test is the shortest test that satisfies both those posterior consumer risks and posterior producer risk thresholds. And so we solve that system equation, and an example of that would be this plot on the left, which considers a C equals 2 failure test. So here we can see those dashed lines represent those risk thresholds at 20 and 30% respectively, and the chosen test time for this 2 failure test is going to be this point marked by the star, which is 95 hours total of testing. And that's the first test time that satisfies both those. So a possible test plan here would be allowing for 2 failures and 95 total hours of testing. Okay, so then after we have our set of test plans, we can compute something called the probability of passing for each of those. And this is ultimately going to help us determine which one of these test plans in our output is something that we should implement. So the probability of passing is the probability that the system will pass future tests. And we've categorized these into 3 different bins. So a low probability of passing is anything less than 50%, and we highlight in our app those test plans in red, meaning you shouldn't pick them. And then also we have this category, which is a good probability of passing, which is anything between 50 and 90%, and those are the ones we recommend picking from. And then additionally, we have marked in yellow anything that's above 90% as a high probability of passing. And so, like I said, we categorize these into these 3 different groups and recommend picking the ones in green. The reason for that is that a low probability of passing the test means that the system is very likely going to fail future tests. And this can happen when your historical data indicates that there's very low reliability. the test plan is just inadequate, meaning that there wasn't a lot of hours of testing that it required, or just your requirements are very stringent. And so this is not a situation you would want to run into, right? You want to pick a test plan that's flexible to your incoming data. And so then additionally, there's a high probability of passing, which may seem intuitively like a good thing at first, because this means that the system will very likely pass future tests. But what we want to kind of get across is this should raise maybe some suspicion to the evaluator, not necessarily a bad thing, but make you question a little bit the output. So this can happen because historical data indicated very high reliability, so perhaps you forgot to include a degradation factor when there should have been. Also, maybe you picked a test plan that just required so much testing that it wasn't even feasible to you to implement. And then also can happen if your requirements are very lenient. And so just to get this point across, if you, for example, picked a test plan that allowed for 0 mission failures and 43 total hours of testing, and you combine that with your DT data that we saw and your requirement, then the probability of passing the test would be the probability of observing 0 failures and 43 hours of operational testing given that developmental testing data. So what we're going to find out once we actually use our app and on this case study is that this is going to give us a very small probability of passing the test. And so that means that regardless of the operational testing data that we see, it is going to be very likely that we make the decision to fail the system because our test plan was so inflexible. It allowed for 0 mission failures. Okay, so I'm going to skip this just for time's sake. Okay, so then now that we've kind of talked about like a little bit of the details of the Bayesian assurance test and why to use it, I want to dive into specifically how you use the app. So this is a screenshot of what this reliability assurance test app looks like. And step 1 is to input your parameters. So the box that's marked historical data is where you'd put, in this example, your developmental testing data, which was a 7 number of failures observed and 329 total hours of testing. The second box is where you want to input those mean time between failure requirements and objectives. Remember from our case study in the beginning, this was 35 and 70 flight hours. The next is the maximum amount of risk you're willing to take, so that posterior producer risk threshold and posterior consumer risk threshold, which we set to 30 and 20% ahead of time. And then this next text box called test plan considerations is how many amount of failures and maximum amount of test time you're willing to consider in that test plan. So for example, if you know ahead of time that your program is not going to test for longer than 350 hours, you can go ahead and input this here, and this means that you iterate over less test plan configurations. So it's going to output a little bit faster the smaller the numbers are in these boxes. It's also going to limit the amount of test plans that you get as a result. And then this last box is the degradation or improvement factor. And here, remember, we knew that there were going to be some system changes from the literature when using DT data to plan for OT. And so this is the box where we include that 10 to 30% degradation factor. You can also include an improvement factor if you think there's going to be improvement from one phase to another. Okay, so this is the output of our app, which is the set of test plans. The first column is the amount of time the test plan suggesting that you test for. The second column is the maximum allowed number of failures in that total test time. And then the third column is the posterior producer risk from that test plan. And so you can see that all of these test plans have a posterior producer risk that are less than 30%, which is good. That's what we wanted. And then all have a posterior consumer risk that are less than 20%. Again, good. That's what we wanted, what we set ahead of time. And then the last thing to notice is that one of these test plans is highlighted in red, and that's the test plan that I explained a couple slides earlier. And that just means that that test plan had a low probability of passing the test because it allowed for 0 failures and 43 hours of testing. Okay, so then the other benefit to my app is you don't just plan for a Bayesian assurance test, but you can also analyze data from a Bayesian assurance test. So if we get this set of test plans and then we choose one, we can go out and we can collect our data using this test plan, and then we can analyze data from that. So suppose we chose a test plan that required 335 hours of testing and a maximum of 11 failures. Then in this case study, what we actually saw after collecting that operational testing data is we saw that we observed 8 failures in this 335 hours of testing. And so what we can do is we can pull forward that posterior distribution from planning as our prior distribution. So our prior is the distribution of the mean time between failure given that developmental testing data. And then our incoming data from operational testing was this 335 hours of testing with 8 observed failures. And then we can also include in our analysis here the mean time between failure requirement and objective that we set at the beginning. So then combining that information, our likelihood and our prior, we can form our posterior distribution to get a better idea of the system's mean time between failure. And so what we see from our app is using the posterior distribution, there's an 80% probability that the true mean time between failure falls between 29.77 flight hours and 57.55 flight hours, which captures the system's reliability requirement. So this is called a credible interval, and that's the area shaded in pink. And then additionally, there is a 73% chance that the true mean time between failure is actually greater than that requirement. And so that's a benefit of Bayesian assurance testing, is we can actually directly compute that probability, which is of interest to us. And so it would be up to you as the evaluator to determine whether 73% was actually high enough to say that that system had good reliability. Okay, so in conclusion, at the beginning, we talked about in this case study that Bayesian assurance test plans can be more efficient than traditional reliability demonstration test plans. We also saw that incorporating previous test data has the opportunity to reduce uncertainty around that mean time between failure estimate, producing those smaller intervals. And then lastly, the most important takeaway is the app I developed provides the T&E community with a simple and convenient way to implement Bayesian assurance testing. And just some final things, some future work that we're hoping to do. We're hoping soon that this gets published to the Test Science website, and we're also working on a paper about this app, which we're going to submit to the ITEA Journal of Test and Evaluation. And then lastly, I also want to mention, if you're curious, the estimated 10 to 30% decrease in system reliability came from this first reference right here. And then if you want to learn more about Bayesian assurance testing in general, I would suggest the second reference right here, which goes more into the mathematics of it all than I had time for today. But that's all I have for today. Can I answer any questions? Thank you so much.
Hello? All right. So if I understood you right, the first reference there is where you got the degradation factor between DT and OT?
Yes, yeah, they gave you an estimated decrease in mean time between failure of 10 to 30%.
And is that based off of like a whole range of DT and OT? Because that seems to be a very important factor, and that actually seems to be the reverse of what we've seen in a lot of transitions from DT to OT testing.
I think it's definitely context dependent, depending on the system you're working for sure. But I think this paper said they got this number from subject matter expertise. But I do agree with you that, yeah, this would be something that would be changed depending on what you're working with. Yeah.
Well, I think it'd be a really interesting follow-up to take some actual DT-OT transitions and seeing if that that factor played out the way we would expect it to. Thanks.
Yeah, thank you.
Hi, nice talk, nice work. I'm just curious, in the DT data, what if they test some amount of hours and then say, oh, you know what, we run out of resource, there's no failure observed, and then they push that program to OT. Like, how would you model that, like that upper limit in the prior?
I would say,
Like, what happens if you put 0 failure in your app? What
yeah,
do you do?
it's not going to do well. You need at least one observed failure. I think we'd have to think about additional ways to model it. If you didn't, the assumption that, your inner failure times are IID exponential, I mean, you don't even have any inner failure times there. So I think that would be challenging. We'd have to think about alternative ways to model it for that case. But yeah, that was a good question. I'll think about that.
Hello? Okay. I have a quick question about the three, the low, high, and the good probability of passing. Are those thresholds something that's standard across the field, or is that something that you guys came up with?
No, those were sort of arbitrary cutoffs by us. Yeah.
Okay.
Yeah, good
Thank you.
question. Yeah.
Just what's the name of the R Shiny app?
Oh, I think it's a Bayesian assurance testing tool or something like that. I don't remember off the top of my head. It's coming
Coming soon to
yeah.
testscience.org. Got it. All right, thank you.
Yeah, thank you.